All right. Let's find all vertical and horizontal asymptotes using limits for this function. Again, for vertical limits, I will accept the, instead of using, for vertical asymptotes, instead of using limits, you can just figure out what makes it undefined. Okay? So the only thing you really need limits for are the horizontal asymptotes. So let's start with that. Okay? We need to find the limits as x approaches infinity of this expression right here. Now, for those of you that were in pre-calc last year, and we did some of this, finding the limit as something approaches infinity. Didn't we only really need to keep the biggest term on the top and the biggest term on the bottom? Because remember, if I have a fraction like this, let's call it x over 2x plus 1. Okay? And I plug infinity here. I would have infinity over 2 times infinity plus 1. Does it matter? Infinity is so large. If I add 1 to it, it really doesn't matter, does it? So it gets to the point where you just keep the biggest term on the top and bottom and you can simplify, right? This cancels with this and I end up with 1/2 and it's 1/2. All right? So with that mentality, I suppose you really don't have to do that. You just got to understand that really adding 1 or 5 or subtracting 2 from infinity, it still stays infinity. So I'm going to take this. I'm going to take the biggest term on the top. Well, actually, let me rewrite this so it looks proper. That's x squared plus 1. So I'm going to keep the biggest term on the top, which is x, and the biggest term on the bottom, it's a square root of x squared. Okay. Now, it would become really, really easy to say this. Well, I know, and what I'm about to write in red, I don't want you to write down. Okay? So just look up here. I can say, well, I know that the square root and the square cancel, so that's 1. And oh my God, if I tried negative infinity, I'd get the same thing. 1/9, so there's only one answer. There's one horizontal asymptote at y equals 1. That is incorrect. And let me explain the reason. All right. If I plug infinity into here, at this point, I would have infinity over infinity squared all underneath the radical sign. Well, if you square infinity, it's infinity. If you take the square root of infinity, it's still infinity, right? So you end up with infinity over infinity. You do end up with 1. But that's not the only answer. Huh? It is, but how come? And I will explain to you in one moment. Now let's try negative infinity. So if I do the same thing here, I do the limit as x approaches negative infinity. And let's get right here, because we're going to get here anyways. We have x over the square root of x squared. You say, well, that simplifies to 1. That should still be 1. Oh, that's going to be so much. There is one difference. Instead of simplifying this, let's plug in our negative infinities. I have negative infinity over the square root of negative infinity squared. What happens when I square a negative value? So negative infinity squared would still be infinity, but it will be positive infinity. And then when I take the square root of positive infinity, when I take the square root of a positive infinity, it's still positive infinity. You're like, well, it's still 1. But no, what's the top? You got it. You got it. So you actually have 2 horizontal asymptotes here, not 1. You have the number 1, but not the quantity 1. Asymptotes at the number 1 and the number -1. We have a quantity of 2 horizontal asymptotes. Okay? So, horizontal asymptotes at y equals positive and -1. Now we got to find our vertical asymptotes. All right? Our vertical asymptotes. So I'm going to take my function. Okay, that would have to be, I gotta find out what value makes this undefined. What value of x makes that undefined? All right, well, we have a fraction. The x on the top really doesn't matter. That can be positive, negative, it can be 0. So let's look at the denominator. Wait, what about the denominator makes an expression undefined? Denominator, yeah, if the denominator is 0, it's undefined. So this would have to equal 0. All right? Which means if I do this right, can I take the square root of 0? The square root of 0 is 0. So what does that mean? That means this whole expression here would have to equal 0, wouldn't it? So that means x squared plus 1 would have to equal 0, which means x squared would have to be negative 1. Is there anything I can put into x and square it so that it's a negative 1? Even if you put a negative number in for x and you square it, it will turn positive. You can never make this expression equal to 0. Therefore, you can't take the square root of this equal 0. There is nothing you can do to make that fraction undefined. Because the bottom will never equal 0. Because we're square. Look it, we have a positive number, and you always have to add it to another positive number. Even if I put a negative number in for x, when I square it, it becomes positive, doesn't it? So when I add two positives, it will always be a positive. I would have to take a negative number and combine it with a positive 1 to make it 0, wouldn't I? I can't make that a negative number. I can't. It's a positive.
Yeah.
Okay. So guess what? There are no vertical asymptotes. There are no vertical asymptotes. How come? Because this can never happen. That can never happen. That's a no-no. No! Therefore, no here. Important. Bang. Let's see if we're correct graphically. We can always, Jalen, verify this graphically if we want. So, I'm going to put our equation into the calculator. I've got x over the square root of x squared plus 1. Let's see my window. I got it in a 5x5 window so it will have a little bit better a picture. It will work on a 10x10 window as well. When I graph that, interesting. We said we have what? 2 horizontal asymptotes at positive 1 and negative 1. And guess what? That's perfect. That's perfect. And we have no vertical asymptotes, do we? We have no line that goes up and down that the function doesn't cross. It goes forever. There is no line asymptote. We're perfect. We're good. We're smart. Yeah? Yeah? Okay. All right. This one's a little trickier because the sign is in there. Sign is in there. I will have you guys walk me through this, okay? So using the property limits, find the limits, okay, of this. We do not need to find asymptotes. They just want us to find the limit. That's it. There is a very simple method when it comes to fractions with the numerator being more than one term and the denominator is only one term. Very simple. I'm just going to break it up into 2 fractions. I'm going to break it up into 2 fractions. Question, if I had x over 2 plus 3 over 2, what does that equal to? Okay, so if I had this, couldn't I break it back up into 2 fractions and it's the same thing? That's exactly right. It's common denominator. So I'm going to break this up into 2 separate fractions. Okay? Using the same mentality. Let's do it. We're going to take the limits as x approaches infinity of 5x over x plus sine of x over x. That is the same thing as this. I broke it down to you guys. I'll act like you don't want to. Thank you. Roby. Okay. Thank you. Pluto. This recording, so I'm going to stop. Plus. Right, so our rules of limits tell us that I can take the limit, if I'm adding two things, I can take the limit of this one separately and add it to the limit of this one, can I? I can. But what can I do with here? Look at this fraction. I can simplify it. I can cancel out the x's, can I? I mean, if I take the limits as x approaches infinity of 5x over x, I can simplify that. That's the limit of 5. And the limit of anything that's just a constant, if it doesn't have a variable, it's just that constant. So the limit of infinity as x approaches 5 is 5. But here's the one that's really going to throw you guys for a curveball. And it's not because it's hard. It's because I haven't explained it yet. Right?
Yeah.
Yeah. So I'm going to take the limit of x approaching infinity of the function sine of x over x. All right. I cannot simplify that anymore, can I?
No.
So I'm going to say it's the sine as x goes to infinity over infinity. Does anyone have any guesses on what that is going to equal? Why do you say 0? Yeah, there's infinity in the top too. But it is actually 0. But how come it's 0? This actually equals 0, which means I'm going to add 0, which means my answer will be 5. But let me explain to you why this, remember, it's when it approaches.
Didn't you say, like, if we multiply it by infinity?
Kinda. Let's take I know this. This I know. Infinity at the bottom is just going to get bigger, bigger, bigger forever. Which means the bottom has to be growing at a faster rate than the top for it to be 0, doesn't it? The bottom gets bigger faster and the top doesn't. It's going to approach 0. So let's do this. Does anybody remember what the sine of x looks like? The graph?
Oh, isn't that, yeah.
It's the x curve, right? So here's positive 1, here's negative 1, here's 0 on the y, but here's my x-axis, right? As x goes to positive infinity, it goes to the right forever, doesn't it?
Yes.
So what happens to sine? Yeah, it goes up to 1, down to negative 1, up to 1, down to negative 1, up to 1, and so forth. What is the absolute biggest value? Sine is going to be 1. What's the absolute smallest value? It is just going to constantly go between negative 1 and positive 1. It will not, sine will never be more than positive 1, will it? So this can be anything from 1 to negative 1, can't it? This goes to 2, 3, 4, 5, 6, 7, 8, 9 million, 100 million, a billion. When you start getting those big numbers and you only have a 1 or a negative 1 up here, that's going to approach 0. Yes. You don't have to be respectful just because I'm recording. Yeah, I'll accept that about it. Thank you.
Good one.
What, do you understand what I'm saying?
Yeah.
Okay.
Good.
Okay. Trigonometry. Fun trigonometry. Now instead of sine, we have tangent. Yeah, I know, a lot of the boos. Boo. Calc sucks. Boo. So describe where all the vertical asymptotes would fall for the following function, where f of x is tangent of x. Who can remember what the graph of tangent looks like? Sine was the s. Okay, I'm going to do a little sketch here. If you want to put it there just for your own knowledge. Yeah, cosine is that bowl or the cup, whatever. So sine of x, we just kind of went over, that's the x. That's sine, right? Cosine of x, well, that's that cup looks like a bowl. Ironically, oh, it's all connected. If you were to take sine, okay, and you were to move that 90 degrees, I'm moving 90 degrees this way, bang. And it cuts this off, that's pretty much cosine right there. See that? It starts with the cup. It's sine over cosine tangent. Actually, interesting fact, if you just draw vertical lines like that, that's what a DNA strand is. Like, exactly, it's crazy. Yeah. So now, let's look at tangent, shall we? Tangents, and if you don't mind, I'm going to erase these right here. Tangent goes like this. Who can tell me? I have 0, I have 90, I have 180 degrees, I have 270, and then I have 360. Better yet, who can tell me what any of those degrees would be in radians?
Oh, would it be
Pi is which one?
pi is 190? Pi is 180.
Pi is 180. Okay, pi. So since 90 is half of 180,
It'll be half
90
of
is
pi. And 2 pi.
okay. Yes, pi over 2. This is 3 pi over 2. And then 2. Everybody's just saying the word pi. Pi, 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 pi. If you look at this in decimal form, this is 0.5 pi. This is 1 pi. This is 1.5 pi. This is 2 pi. And this goes up by a half every time. It is. But this is math, and we make it difficult, so it's a fraction. But yeah, it's a lot easier that way, isn't it? That's why I showed it to you. Because you can look at this and be like, oh, I know that's half. I know that should be 3 halves. So if you had to know what 450 degrees is, you just add another half to this, you 2.5 pi's. Which on the test is still correct. Okay? So now, tangent. Green. Is everybody okay with green?
Yeah.
Okay. Now, tangent starts just like sine. Remember, it ends, if I'm doing this at 360, just like sine. And in the middle is just like sine. But it is slightly different than sine. It starts going up and goes up forever, down like that. Up and to the right forever. And down and to the left forever.
Oh!
Yeah, your O's are correct. And there's an asymptote at 90, and there are an asymptote at 180, and it would keep this pattern going. That's what I meant. I'm glad you're paying attention. That was a test. It's at 270, not 180. And if I were to keep on going forever, and this would go down and to the left, and up and to the right, and up and to the right, and down and to the left, and I would have asymptotes. Sorry, they're slanted. What would this degree be? Close. 450. Every time I'm adding 90, right? 90, 180, 270, 360, 450. What is this degree? 540. What is this degree? 630. So, they're asking us, where are all these vertical asymptotes happening? Well, it starts at 90, and you go up by 180 every time, right? And likewise, if I go backwards, it's the same thing. It would be at negative 90, negative 270, negative 450. So, there's no really great way to write that. You're going to say 90, 180, or yeah, 270, 450, and so forth. And comma would be negative 90, comma, negative 270, and so forth. Or, if you want to write it in pi, you say 0.5 pi, 1.5 pi, 2.5 pi, and so forth. That's where all the vertical asymptotes are.